Hello, and welcome to the third and final session of the MOSA Virtual Summit, applying a MOSA strategy across multiple domains. My name is Emma Helfrich, Technology Editor with Military Embedded Systems and moderator for today's event. To learn more about military embedded systems, please visit militaryembedded.com and check out our articles, blogs, and podcasts, all covering military technology. Our speakers today are Mark Littlefield, Senior Manager of Embedded Computing Solutions at Elma Electronic, Anish Katari, Vice President of Marketing at Systel, Craig Powell, Director of Business Development for the Army at Systel, Robert Power, Field Applications Engineer, West for Mill Power Source, and Jason DiCharo, System Architect and Product Manager for Curtiss-Wright. Session 3 is sponsored by Elma Electronic, Systel, Mill Power Source, and Curtiss-Wright. The MOSA Virtual Summit Platinum sponsor is RTI, and the event is hosted by Military Embedded Systems and Open Systems Media. Before we begin, I have a couple of housekeeping items to go over. This and all Open Systems Media virtual events are copyrighted and may not be recorded or used in any way without the express written consent of Open Systems Media. The session will consume about 40 to 45 minutes, leaving the remaining time for the question and answer portion. You'll find on your console window an area where you can enter your questions in real time. If you have a question pertaining to the event operation itself, one of our technicians will get back to you during the session. We encourage you to ask questions throughout the session while the questions are still fresh in your mind. We'll address as many questions as we can during the closing Q&A portion. If you have a question for a specific speaker, please note so at the beginning of your question, or I will offer the question to all of our speakers. Please note that as much as we'd like to, we may not get to all of your questions today. In that case, someone may get back to you after the event with more information. On the console, there's a handout section, and that's where you can find the slides being presented today. This session and the overall event will be archived online at the URL shown on your screen and be available within 48 hours. Once up, it will be available for exactly 1 year. I'm pleased to turn it over to Mark Littlefield of Elma Electronic to get started.
Hi, thank you, Emma. And welcome everyone, and thank you for attending this afternoon. I'll be talking today in our theme of multiple domains, MOSA across multiple domains, about small form factor computing in MOSA and some of the work that we've been doing in VITA and within SOSA. So SWaP, as everyone knows, constantly drives defense electronic system design. It's been doing it since the dark ages, and it's still doing it today. In the distant past, everything was custom. Everything was designed specifically for that particular application with those particular constraints in mind. Looking forward, we started getting in the early to mid 1990s, the off-the-shelf components, VME, compact PCI, ATCA, other board form factors. Today, the primary go-to board form factor for these kinds of systems is VPX. But what we saw in the past was that there was often incompatibilities between products, largely between different vendors, different suppliers, but even sometimes within a supplier's family of products. And that would cause a lot of trouble both in integration and design, as well as creating vendor lock for systems. And MOSA is a set of initiatives to really break that open and say, we need to make these much easier to integrate and much easier to upgrade when the time comes to do technology upgrades and things like that. The expectation is we should be able to pick COTS components that are designed to work together, that they just work when they're put together. So the problem is that there are systems that are in form factors that are physically smaller than what VPX can support. There's some examples that are pretty well known, common launch tube applications like Coyote UAV, and there's actually a bunch of different UAVs that are compatible with common launch tube. There's CubeSat, which gets a lot of attention for space applications. One specific example is Cirrus, which is a range instrumentation system from Rockwell Collins. Traditionally, folks have had to designed custom solutions, or perhaps they applied proprietary solutions like Elma's small form factor boxes. But that was pretty unsatisfactory, and it really isn't sitting well with the whole MOSA approach to modular open systems architectures. And SOSA identified this problem pretty early and has taken steps to address that. There's a small form factor subcommittee in SOSA that was formed in early 2020, and its charter is to define small form factor content for the SOSA technical standard and to ensure that that content is in alignment with SOSA principles. And in fact, if you download the 1.0 release of SOSA, you'll find the first of that content in there, and I'll be talking about what that content is. Some of the principles, there's a lot of principles to SOSA, but some of the ones that directly affect small form factors, things like modularization, scalability, interoperability, replaceability, the ability to take out a module, put another module of a different type with the expectation that it'll just work. And it also needs to be able to support all of the SOSA missions that are defined. Things like EOIR and SIGINT and comms and radar. Whatever the solution, it had to be able to address all of the missions that are defined within SOSA. So two came immediately to the front. Well, the first thing we did was we did a trade study. And what we found was that there was no obvious form factor that met all of the criteria, especially scalability. But two paths emerged. One was a short VPX, and the other was based on VNX or VITA74, but with some considerable enhancements. Short VPX was very easy. It was just taking the 3U VPX and shortening it from 160 millimeters to 100 millimeters. And we also increased the allowable pitch size, the thickness of the boards, to put more functionality within a single slot. This did, in fact, reduce the size that VPX required for some smaller systems, but only about 30%. It also allows reuse of VPX infrastructure. It was a very easy thing to adopt. But again, that it only reduced things about 30%, which wasn't enough for some of the key applications we were targeting. So then we turned to VNX. VNX is significantly smaller per slot than 3U VPX, about 70% smaller on a per slot basis. It's a reasonably good fit with SOSA attributes of scalability, modularity, and such. It supports both backplane and cable connections, but significant enhancements were needed before it was really ready for SOSA. So some of those things that we identified was lack of slot profiles. There's no apertures for coax or optical blind mate in VITA74, no defined support for VITA 46.11 out-of-band system management, no defined power modules, and there was no way to use wedge locks or direct surface mounts with the modules. They all had to be packed in a box, and we wanted more flexibility than that. So we've started VITA 90.x to capture all of these things. I'm going to talk a little bit about some of the key things that have already been captured in VITA 90. So first off, taking the original 19 millimeter module that we had, we kept that same 400 pin connector, but we added two additional connectors, a 320 pin with a half aperture and a 240 pin with a full aperture. Then we defined aperture fill blocks for those apertures. Specifically, we defined three of them. A full aperture hybrid, which includes two optical MT connections with 2 by 24 fibers. And coaxial connectors, 16 size 20 and 4 size 16 connectors in that full aperture. And then we also defined two half apertures, one that's dual optical and one that's a hybrid of optical and coax. From there, we stepped up to slot profiles. We defined what we would say a common template, if you will, of a payload profile across all three connector types: the 400, the 320, and the 240 pin connectors. They have a common utility segment, S0. They have a common communication segment, S1, and then they've got a variable section that's a mixture of copper or overlays or both. In the case of the 320 pin connector, that allows us to do more specialized profile definitions. From there, we stepped into some of the more specialized slot profiles we would need. We defined two switch profiles, one that's has no aperture, one that uses a half aperture for optical. And then we defined two radio clock profiles. One that's an entire profile of radio clock and aux clock, 22 actually pairs of ref clock and aux clock. But then we also made use of that SBC template that we defined and created a smaller clock, a radio clock that combines SBC functionality and clock functionality using the 320 pin template and the half aperture that gives 7 ref clocks and 7 aux clock pairs. We've proposed alternate mechanicals using wedge locks and feet width mounting holes so that things can be mounted to, say, sidewalls or to bulkheads within aircraft or ground vehicles. These are for things where a box just simply won't fit right and you need to distribute your computing inside the platform. This has been proposed. It hasn't really been balloted and hasn't really even been debated yet within the VITA 90, but it will be in the not too distant future. So we do have some work outstanding. Short VPX both provide powerful platforms for small form factor MOSA SOSA applications and following MOSA SOSA principles. Short VPX is complete. It's in both VITA 48.2 as well as in SOSA 1.0, but the VNX Plus needs some more work, and our goal is to have that work done in this calendar year, and we can expect to see the first aligned products in this year. There's folks working against these draft VITA 90 standards that are in work right now. So in summary, what we're doing here will give suppliers the basis to create modular building blocks to support much smaller SOSA, MOSA-based systems that's currently possible. And that's across all these different domains that we support within SOSA. Most importantly, these solutions are 100% alignment with SOSA technical standard principles and criteria. And so there's no reason why they can't be applied in any of these domains. And with that, I'm going to pass it over to Anish and Systel.
Thanks, Mark. Good afternoon. Thank you for joining us today for this discussion on MOSA for multi-domain operations. Thanks to Military Embedded Systems for bringing us all together today. We've enjoyed some terrific sessions so far, including what Mark just presented, and we hope to be able to add to the knowledge pool from our perspective. My name is Anish Katari. I'm here today from Systel, joined by my colleague Craig Powell. I'm speaking to you today from beautiful Sugar Land, Texas. A little rainy, but still beautiful, where Systel is headquartered. Systel has been designing and manufacturing rugged computing products and solutions for 33 years for defense and industrial enterprises worldwide. We believe OSA and MOSA implementations should utilize a multi-tool approach, ensuring the best possible capabilities in the hands of the warfighter at the optimal cost to the taxpayer. So that's what we're going to focus on today. But before we dive into all of that, I thought, even at the risk of covering well-trodden ground, that it would be good to start at the start. So what is MOSA? So the U.S. DoD has embraced a multi-domain warfare doctrine across the services, and central to this strategy is the concept of MOSA, or Modular Open Systems Approach. And while this concept has been around for many years now, it's really become all-encompassing over the past couple of years. And the goal is really utilizing open and common standards to more effectively acquire, design, integrate, deploy, sustain, evolve bleeding edge technologies and capabilities. And as outlined here in the Tri-Service memo that's on the screen over to the right from 2019, this is a warfighting imperative. DoD has to keep pace with the commercial sector and is increasingly partnering with industry very early on in the development cycles to adopt and deploy the latest COTS technologies. Open standards and MOSA is the key to successfully achieving this. So as we've already covered and heard about today, there are several standards that have really emerged and gained widespread traction under the greater MOSA umbrella. So including, but not limited to what's on the screen here today. So SOSA, FACE, HOST, Victory, MORA, CMOSS. We had a great CMOSS keynote presentation this morning. But what we're going to talk about here in the next few slides, and what Craig's going to talk about here in a minute, is that there are other MOSA-aligned, open and common, widespread architectures and standards that must be considered and used, along with the ones listed here, to best support the MOSA mandates. Again, with a multi-tool, best tool for the job kind of approach. So MOSA is absolutely critical, and it's absolutely foundational. So in today's modern battle space, there's a proliferation of HD sensors collecting just mountains of never-ending data. Actionable data is paramount to what JADC2 and the concept of JADC2 is all about. Creating, executing that data at the nodal edge, and really feeding it into the JADC2 ecosystem. So this idea of a JADC2 unified cross-domain architecture, it's breathtakingly transformative, but that transformation, that transformative characteristic has to reside on a stable foundation. And that stable foundation is what MOSA is all about, and it's really built around MOSA and the concepts within. The idea of open, affordable architectures and standards. I'd like to turn it over to my colleague Craig now. He's going to discuss the drivers and benefits of MOSA and how adopting and utilizing a multi-tool approach to MOSA can be very impactful. Craig?
Thanks, Anish. So I'm going to spend the remainder of our time talking about MOSA and the other open system approaches that are supported within that infrastructure. So when you distill down the 10 or 12 different current open systems architectures or approaches that are out there, they all distill down to a common theme, and specifically down to a common feature or a common driver. That would be a modular design. So the ability to use major system interfaces, not only on the platform, but to support down at the component level. The second common feature are the standards, the widely used and consensus-based standards. This of the three is probably the most critical. And then finally, the system architecture, the ability to add, remove, update architectures within your, let's say, your computer, within your system. The benefits of that are costs. So they are significant cost drivers as far as driving them down by going with a commercial open standard type capability. The ability to acquire, integrate, and deploy is reduced. The ability to carry out tech refreshes. And then finally, the interoperability. And if you base your architecture on consensus-based standards, the interoperability is not that critical of an issue. And as Anish had mentioned, interoperability in an ecosystem is critically important because you'll break the network at your level if you're unable to function within that total domain. So MOSA, again, there's a lot of open systems that feed into the MOSA architecture. So we thought, let's go brief Mrs. Morgus at ASALT and make sure we're on the right path. So we asked two questions. First question was, does our interpretation of MOSA make sense? Is it accurate? They came back and said, yes, it is. Next question is, our design philosophy, does it meet the basic tenets? Does it meet the philosophies of MOSA? And their answer is, it does. They agreed with our structure. So I'm presenting two different examples here. So MOSA isn't specific to one single computer architecture. It's based on a consensus type architecture. So when you look on the left, those platforms all had completely different tactical swap requirements, but they were all using and carrying out the same sort of mission set within that computer. So because we adopted a MOSA philosophy in our design, we were able to accommodate the hardware to fit within that infrastructure. And if you move over to the embedded side, same thing with our smaller embedded computers. The ability to adapt and add capability in a very rapid process is available by employing MOSA, or an open systems approach. I do want to say one thing. Do not be afraid of MOSA. It is intimidating when you go through all the documents, when you go through your SOSAs, your GCIAs, your saves. It is intimidating, there's no doubt. But look, the bottom line is there are options that meet the MOSA requirements. You do not have to be stovepiped into a single architecture. You have VPX. The speaker previously talked about VNX. There's COMI, there's ATX. These are all common accepted standards that are currently used not only in the military, but also in the commercial structure. So specifically, I want to talk about two things: affordability and adaptability. The approach that Systel has taken is we use a architecture that's either ATX or COMI base, which again are both accepted under, for example, GCIA, which is the PO GCS Common Infrastructure Architecture, specifically in their single board computer definition. So both in a common compute and at the crew station compute level as well. So our focus when we design our systems are affordability and adaptability. Following on the smallest form factor. So we can change our form factors from a exterior perspective because we use a common standard board, which in this case would be COMI, which it gives us some affordability to change the exterior to fit the space claim that this box potentially is going to go into. I call out smallest form factor, and that is a play on words a little bit. And somebody had asked the question, do only conduction cooled or air cooling available? Systel will build the system as small as I can cool the system. So for example, the Kite Strike, which is a computer on the left, it uses a combination of conduction and convection, removing air over the exterior fins opposed to over the circuits. So we've optimized the convection piece, which from a exterior perspective fits SAVE. So you meet that MOSA requirement, and you also answer the mail on GCIA. And then finally, being able to do it in an envelope or in a package that's reliable and rugged. Now, when we talk about this, when we talk about the MOSAs, there are other critical variables that are impacting your decision matrix. Swap 2C is a huge issue. I have a space claim. I have to be able to get this box in, and the user has 2 GPUs in it, and I have to be able to cool it. Then on top of that, I have to build it rugged enough and to support the Victory standards specific to Ethernet and some of the other network requirements. I have to have the security level either from a commercial solutions for classified, and that would include things like encryption for data at rest and examples like that. Then taking that one step farther, which is something we just started doing recently, is leveraging open systems like the NVIDIA JCEP, which is a functional safety capability that's used on current commercial autonomous vehicles, leveraging that into our systems as well. So again, from a true MOSA perspective, our philosophy is to leverage as much as we can from an open standard at an affordable and an adaptable level. And that wraps it up. Anish, did you want to do a quick closer on the last slide?
No, just thank you very much for attending and listening. We're very excited to be part of this conversation and really, be working in partnership with industry, government, really all of the players to really push this forward for the best possible capabilities. I think we're going to turn it over now to Robert at Millpower. So Robert, please take it away.
Thank you, Anish. Yes, I'm Robert Power, and with Millpower Source, we are a manufacturer of power supplies. One thing I'll get off the table real quickly, yes, it really is my name. It's okay. It's an old Irish surname, so that's not my stage name or anything. So we were tasked today with trying to talk about how different how the VPX standards work across the different domains that are presented across the different branches. So we thought we would talk about how this works in different equipment types, but also with regard to the power standards that are involved. So we, of course, have seen this progression here with SOSA Face of Victory now falling under this MOSA standard. I won't belabor this because you guys have talked about this at length here, but most of the previous work, especially with CMOSS and Victory that came with it, hosts and OMS, all of this is finally now collapsing and moving into SOSA. And but as we worked with the SOSA technical standard, started to develop it, it became clear that since it was originally an Air Force standard, it focused mostly on airborne sensor pods. So, and as we started looking at it from a power perspective, we started to notice that that more needed to be done as far as bringing in some of these other standards that we'll talk about when it comes to the branches. So, but most all the open standards there are truly moving into SOSA alignment. And one of the things that I did learn from SOSA I thought was interesting is that they define a sensor as anything that puts out a signal and receives something back. Basically, that's it. So that's a lot of things actually. So there are various groups inside the group that you'll see different task teams. So one of the things that has happened as a result here is that there's been a great improvement in VITA standards. Particularly, a lot of the old VITA standards have, as time went on, they started to develop lots of permissions, and basically you got to the point where you could almost drive a truck through those standards, and so there were some interoperability issues. And I think that's what everyone wants here as we go along here. It's not that we're ever going to get the plug and play, as it's been explained to me, but we certainly get the plug and integrate. That's a reasonable sort of goal. But as we move towards stricter standards and tightening up of some of these things in the VITA standards, we'll get better interoperability. So, and really, one of the things that also happens is the formation of SOSA. So I've been told by the VITA guys is that they constitute the largest collective customer for VITA standards. So they really have the ability to drive VITA standards, and as a very powerful group. But SOSA does want this interoperability, and it's really forcing these kind of improvements to achieve that. So one of the things we've noticed from our end, from making power supplies, which is our interest here, is that these legacy 1235 power outputs for VPX in particular, they're kind of problematic in a lot of these new systems. A lot of these processors, GPUs, incredible amounts of power, especially as things were 5-volt based. And what happened is we had lots of backplane currents as high as 200 amps that were being spec'd in. And many times you had to add an extra power supply card, really, just to get to those high currents, only for the 5 volts. Terribly wasteful. But it was also difficult, really, for users, for our customers who are trying to put a rack together to assess their total power needs. We never knew which one of those, the 12, 3, and 5 might pop up as a high requirement, and forced a lot of these things on us because we had to accommodate all these things. So these different power needs. So moving to 12 volts only allows for a lot better simplicity. At least now we understand how much power you're drawing. But the bottom line also is that there's a lower backplane current. So no more will we have these 200 amp currents going across the backplane. And the assessment of power is much simpler now. And really, it's a lot simpler task to determine how many PSU cards you will need. And this has all been made possible because of these payload cards. They can realistically use 12 volt regulators instead of 5 volt ones on board. So all these things have been made possible. So some of the great improvements in semiconductor technology. So SOSA is also not only about VPX. Yeah, it's a large degree it is, but and Mark has been talking about the small form factor initiatives. One other thing that SOSA is doing is they are trying to determine which connectors are being used at the box level, and they've determined about 5 different classes of sensors from less than 6 inches up to above 19 inches. And the upshot of this is that connector types are now standardized. Which helps all of us here as it drives connector suppliers to shorter lead times by sheer stocking. And one of the great points about this is that in all of these cases, only the interface is being controlled, not the IP inside. So that does allow us to all compete on on our own, not just IP, but swap different types of special features that may come inside there. So and as we mentioned before, SOSA is working on these small form factors. But SOSA also now lists these military power standards inside. That's one of the things that we've improved in the latest snapshots. But the platforms, of course, will define usage and the various power levels. So let me go through this real quickly. We thought it'd be educational just for a lot of you to kind of see where we understand this and how power has the way to unify things. So each of the branches actually has very diverse equipment types if you think about it. The Navy they have vehicles in addition to ships, subs, and aircraft. The Army they even have ships in addition to what's known in the vehicle world and their aircraft like helicopters. And the Air Force even has some vehicles and some ships. So it's not always clear that the power standard, the certain power standards come from each of the branches. Some of them use these things depending upon the equipment type that they have. And then, of course, we've got all these unmanned systems here: UAVs, UGVs, UUVs, USVs, all these things that are unmanned that may use various types of power, regardless of the branch it came from. But the common thing that we see is that all of them have AC generators with dirty, nasty power outputs that have to be cleanly regulated. Our job really is to provide all of you with nice, regulated, clean power you can use on payload cards. So that's what we kind of see is one of the things as we were working on the committees there, is the power systems actually been somewhat unifying factor trying to develop these SOSA technical standards. There are different types of, one of the biggest ones that we see out there is MIL Standard 704 that comes out of aircraft needs. And I've just put this, this is really too much to go through, but these are the common ones that are being used. The 3-phase 400 hertz, very common, and lots of 28 volts and 270 volt for DC supplies. Those are the most common ones that we're going to tend to see from a power supply standpoint. And we have to also mention DO-160. This comes from the FAA, but a lot of those there are a lot of specs coming out of DO-160 now that, for instance, the most common lightning specs we see come out of DO-160. But these are the common power types they have, very similar to MIL Standard 704. But there are lots of, just to say, there's lots of overlap between these two needs. As there are more shared airstrips, for instance. Between shared airstrips that share military and commercial use. And one of the big challenges that we found is that these bus transfer switches on some of these aircraft, they have chatter issues. So sometimes it takes a switch a little time to close. And so you can actually interrupt power and have really large, terrible power interruption times of like 200 milliseconds, 50 milliseconds. Both DO-160 and MIL Standard 704 can have these types of chatter. And so the solution here is, short of having something really large, is to add small holdup modules across the system. So we have these, and so one other thing that we find challenging with airborne systems is, particularly with AC systems, is a lot of the aircraft need lagging power factor. Mainly because of these very inductive generator outputs. So as you learned in school, a lot of us learned in school that it's great to have high power factor. Yeah, it's true, as long as there's not something really inductive looking at you upstream. And inside your home, for instance, they tend to treat the power factor out at your substation. So you don't have that problem in your home. But that's very much a problem on aircraft and on some ships. So this is one challenge. We would add some of this type of lag back in there. So And without that type of control, if you don't put any control on an AC to DC, you generally have a leading power factor, which is really usually not good for very many people. So that's a solution. Most of us are doing this, but they're adding a PFC stage and possibly some inductance here to give you that lagging power factor. Another one that we have for vehicles is Mill Standard 1275. This was not in SOSA until the last snapshot. We started really addressing this. And really, it's very, very targeted, 28 volt systems only. Now, vehicles all have batteries, and which act as a large capacitance. And the funny thing is that when the battery fails open against an unregulated generator, you can have output pulses of 100 volts that are running all the time. So the power supplies, any downstream devices, anything running off of this needs to be able to survive it. So you're allowed to clamp this off because there is some impedance listed here in the spec, so you can actually design some clamp circuits to take care of it, but not always. Not always is that practical. So, by the way, just a point of note: this load dump phenomenon actually happens in your car all the time. Have you ever noticed that many times I know most of the time when my car is stalled out from a dead battery, if it's dead, all of a sudden. And that can open up. That battery has now become open. And what was happening, I didn't know, unbeknownst to me, is I was probably getting 75 or 100 volt pulses across all the electronics in my system. So we have to design it against this kind of thing. Just as in your vehicle, you take a dim view of all of your dashboard being blown out by a dead battery. Vehicles have the same sort of challenge. And this is just another slide describing it. So we have to survive 100 volts. Now, Mill Standard 704 for aircraft, it also has 28 volts. So it's not the same at all. It has only a 50 volt requirement, but you can't clamp it. That's one of the rules. And so all your devices have to be rated for a little above 50 volts. So from our standpoint, from a power supply perspective, this is a big difference. And so we have to address this. And finally, we have Mill Standard 1399 for naval. This covers all AC power. U.S. Navy's long had problems with inductive generators, and they're also the ones that invented power factor control. So you can credit all that to them. This poor power factor can cause high neutral currents, so they use lagging power factor. They also have terrible generator specs that be presented that have to be protected against. And they too also have the power transfer situation. So I'm going to skip over this. One of the things that we have seen is that now power supplies are also managed by the 46.11 system management. So just like all the payload cards. So we have tier 1, 2, and 3 are allowed now, but ultimately everything's going to be tier 3 only. And it's just simple monitoring power levels, fault conditions, and it's supposed to be self-configuring. That's what we're working on. And there is a possible movement to some really advanced system startup and diagnostics. So really, just in conclusion, we're working towards a full interoperability. But one caveat: just notice that the VITA62 power supplies cannot be mixed across vendors, just for current sharing reasons. Ours will not share with someone else's, and that's just a limitation of analog power. But all of us, PSU vendors, we are going to compete on efficiency, ruggedness, and all kinds of swap. See, all this is healthy competition. We kind of view it as something really good for the defense industry and something that's long been needed. So I'm a little over time. I'm just going to go and I'm going to transfer this right off to Jacob Sealander at Curtis-Wright.
Hi, this is Jason DiCharles from Curtis-Wright, talking a little bit about how to apply MOSA strategy across multiple domains. So we heard a little bit today talking a lot about individual platforms and hardware that go on a platform. What we wanted to step back and say is, how do we share information across the battlefield domains? When we talk about battlefield domains, we mean things like maritime, land, air, and cyberspace and space. Physical domains, and getting information from, for example, a UAV flying in the airborne domain through the cyber domain to a land domain and artillery battalion that maybe want to put trying to hit a target, and they want the feedback to know if they need to adjust fires or anything like that. So how do you really take what we have today, which are really stovepiped individual systems that don't communicate well with each other, or platforms that have to have multiple systems on board just to be able to see the pieces of battlefield that somebody thought ahead of time that they would need to talk to. And then, of course, there's value in getting information from the other domains, and it can actually increase your ability to fight the battle that you're facing in front of you. So looking at examples from the commercial world, we kind of look at the way that the internet is designed and the transition that we're going from Web 2.0, which is more very, very similar to a stovepipe architecture where you go to one company for a service. For example, you go to Google and you want to use Google storage. Well, you can't easily transfer that information over to Amazon service. It's a competing service. When you go to the newer Web 3.0 architectures, there's open standards and communications that span all the different vendors. So you can, you don't necessarily care or know who's storing your data, but you're doing it in such a way that it's also secure because you can shard the data across multiple vendors now. So applying those sort of methodology with the open standards across the communication domain really gives you the ability to take advantage of all the domains on the battlefield. So in order to implement that, you have to then tie your different hardware platforms together in really a tiered fashion. So you would have your cloud compute, which would be a larger data center or ground data center somewhere that has massive amounts of compute capabilities and storage capabilities and can see the entire battlefield. You have more forward deployed portions called the fog computing, which is where you'd have, for example, maybe a large aircraft that can carry a lot more hardware and compute capabilities. And then further down, you have your edge computing, which would be more like what your soldiers would be carrying, for example. Think of it like a cell phone today, where it can reach all the way back through the chain and get the data and the information that's required at the time to complete the mission that they're being asked to execute. So using this technique and these open standards and the methodology that's being adopted in the commercial space and applying that to the battlefield really is a way to connect all of the different pieces that we have out there today and will have in the future, and really give us the ability to increase the effectiveness of each individual piece by leveraging everything else that's available. So that was a very high level kind of introduction to how you would do that. Unfortunately, given the broad range of this audience, I can't really go into more details of how you would do that, or at least I'm not comfortable doing that. So Curtis Strike does offer services where we can help you in your specific examples, in your specific programs, implement these open standards and how to architect your system for your application to work with other systems on the battlefield, and really want to offer that up as a service to anybody, so we can help you be successful. That's what I got.
All right. And a big thank you to all of the experts for those super informative presentations. I'm learning a lot, and I hope everyone in the audience is as well. And we will now enter the Q&A portion of the event. We got a lot of questions coming in that Q&A chat over there. So I will start off and begin with the very first question we received for Mark Littlefield. The question asks, so SOSA SFF modules will be only conduction cooled, or will they also be air cooled?
So that's a great question, because we're specifically defining the VNX modules and at the module level. That is that case that you saw in the picture with the one with the credit card on it. That's what we're defining. We also, though, defined inside the natural heat paths, the natural thermal paths through the electronics and through the casing of the module, with the idea then that the integrator can add whatever additional cooling paths are needed within the chassis or within the vehicle that it's being deployed into. We've got, you, for instance, in the photos in the slide deck, there's boxes with heat sinks on the side. You might also have like a single slot with big cooling fins on it for an air-cooled application. You might want to do like air flow through, where the slots in the chassis have air gaps between them to allow air to flow through in between each of the individual slots of the VNX modules, and that way gain extra cooling. We did some modeling and showed we could cool up to about somewhere in the range of about 30 watts per slot by cooling in that way. So it really was designed to give the integrator the flexibility to choose what kind of cooling they want to do for whatever kind of environment they're deploying in.
Very cool. And seems like a theme here is flexibility. So that seems to fall under that category. And another question here I'll delegate to Craig. Does MOSA have a global influence, or how would you describe the influence it will have on our NATO allies?
Sure. So I would say it does for a couple of reasons, and both directly and indirectly. The international influence you're seeing in things like GCIA are common to things like NATO Generic Vehicle Architecture, or NGVA. So, not only do you see it in very specific military-like standards, but I think with the fact that SOSA and its parent organization, the Open Group, which are international organizations, and the fact that we must be interoperable does mean that it definitely does have an international piece. And on top of that, to support that argument, Anisha just sent me a link to a story. Project Convergence is trying to involve NATO partners in that activity to ensure interoperability, to ensure things like coalition shared databases allow everybody who can access it to actually extract data from that capability. So I would say it does in multiple different flavors.
So Emma, if I could add to that, with SOSA, while SOSA is a US only organization, there's a great deal of attention being paid to it by our NATO allies. I've personally spoken with people from UK MOD as well as integrators in the UK, and I've been peripherally involved with folks in other NATO countries who are watching very carefully and making plans about how they can adopt SOSA for their projects.
Right, absolutely, because I imagine the joint domain will extend beyond domestic efforts as well.
Well, and the benefits to be gained are not limited to the US. They can benefit from the standards as well as anybody else.
Absolutely. And we'll move on to that next question, and I'll direct this to Robert. One of our audience members says that they see a trend toward software-defined power supplies for flexibility and wants to know your thoughts on that and whether or not you have any pros or cons.
Well, I spent some time in servers where they do have those types of adjustable power supplies. Number one thing is there are limitations to how much you can adjust, but one of the things that people are starting to think twice about is having that much flexibility on something that could have be cyber attacked. So cybersecurity, believe it or not, is becoming a big thing in power supplies. So I would actually say in defense systems, at least, it's working a little bit against that. I know we have to provide certificates of vulnerability just like payload cards do. So there is some concern about that. So sounds great. I'm not sure that that's what people really want here. That's my thought.
Right, very interesting. And we have a general question here, and I'll direct that to Jason if you'd like to take it. One of our audience members asks, does MOSA/SOSA have applications for space besides, the tri-service, Army, Navy, Air Force?
Well, yeah, sure. So you can standardize on communications protocols like we talked about through the different domains, but there's also, if you can standardize across hardware, across multiple platforms, there's acquisition benefits to that, as well as standardizing on form factors.
For sure. Would anyone else like to touch on that one before I move on?
Sure, I'll mention a plug for VITA. That VITA 7, I think it's VITA 78 is Space VPX, has been very active in the last months, and Space VNX, the VNX Plus rather, the 90.4, if I'm not mistaken, I can't remember, but they are really gearing up right now to bring these kinds of principles to the space domain. They want the same benefits that everybody else is getting from MOSA approaches.
Absolutely. And I have another question here for Robert. Mill Power Source also does a lot with custom power solutions. Are there instances with systems such as with Vitronics refreshes where a MOSA solution will be a part of a custom design? Custom and MOSA solutions have to coexist on some level, correct?
Yeah, that is correct. There are lots of cases where, in fact, we've actually never seen anything that we don't have to customize in some small degree. The point of SOSA, it seems to us, is that you're really just trying to standardize the interface. There could be things. Someone else asked another question here. I'll just answer it. That about the different input ranges, things like that. There are all kinds of things, at least from our standpoint, we have to have to unify them and bring them into a form factor. But there will always be extraneous things that we can't control. There are going to be things like environmental things where we can't standardize that. That comes from the platform people. There are lots of things like this. So yeah.
For sure, keeping you on your toes. And I'll direct this to either Craig or Anish because the question surrounds common control stations, and sometimes that's just a tablet. So to both of you, in what ways would you say MOSA will affect the common control station, if at all?
Go ahead, Craig.
There is in GCIA a section on what they call crew station compute, and it does call out the standards that are advisable for the crew station. It includes everything from communications over Ethernet or serial, and then video over, I can't think of the formats, DVI, maybe GigaVision, so an IP stream of some sort. So there's definitely a reference to MOSA that calls out crew stations. I don't know about tablets, like the dismounted ones. I haven't come across, but I'm sure there is something referenced in one of the open standard documents.
For sure. And as those control stations get smaller and as other capabilities get smaller, I'll direct this to Mark. Which SFF looks more promising for SOSA adoption, VNX versus short VPX or other?
I think that either one is completely a suitable design approach. Depends on what your needs are and what is available on the market. I think we're just starting to see the first short VPX products hit the market. They can leverage the same backplanes as the typical longer VPX. And so it's a quicker path to deployment. And if it works fine for you, go with it. If your application requires something smaller, then VNX Plus might be the better choice. It really depends on what you need.
Absolutely. And the options are out there, it seems. And for Jason, here's a question for you. Are you seeing requirements in new programs and refreshes calling for CMOSS compliant or SOSA aligned solutions?
Yes, both actually are seeing requirements being flowed down to existing programs as they go further through, like at the PDR and CDR level. They're asking for those requirements to be implemented going forward.
Perfect. And Robert, we just got a question in for you. We're seeing a rise in integrators using non-VPX power supplies for VPX systems due to the high cost of VPX power supplies. Does MilPower offer such options or see paths to cost reduction of VPX power modules?
Well, yes, there are some people who don't have any space. They cannot allocate a slot for a power supply. We see that a lot. Sometimes we have to put something on the side of it or put something even outside of it so that they're allowed at least to fit in their application. So if anything has to go, it's probably going to be a power supply. So we may have to mount it somewhere else. So absolutely, yeah, we have some options like that.
For sure. And this one I know Mark was interested in, but it does seem pretty open-ended. It's more of a comment than a question that I believe the audience would be interested in hearing all of your takes on. So the audience member writes, just the idea to standardize VPX profiles to increase interoperability and avoid vendor lock-ins is great and required also in industrial VPX applications. Also, many other industrial requirements are similar. And they assert that MOSA shouldn't focus on just military/defense/airspace. What are your thoughts on that?
So yeah, I'll kick that off, and I think this is a great one for everybody to comment on. This is actually one of my favorite topics, in that what we're doing is not just limited to defense, and it's not just limited to those programs in which, like, for instance, have a SOSA requirement from their customer. You know, anybody who does these kinds of systems can benefit from these standardization efforts. And I encourage people to look at the standards and think about how you can adopt it. What we're finding is that we're building a market here, a market of components that people can mix and match to be able to solve their problems. And the more that market grows, the more competition there is, the lower the prices are going to drive, and everybody wins. You know, the market grows, suppliers sell more product, prices go down, everybody wins. So yeah, I think whoever asked the question is exactly right.
Very interesting. Anyone else want to add anything?
So, I mean, I'll speak to it just for a second. So agree with Mark completely, and you know, with the comments, the commenter rather, on you know, focus of MOSA and maybe SOSA specifically, but maybe MOSA generally, on more than, you know, let's say just aerospace defense applications, wider industrial commercial markets. I think it makes sense. I think it talks to some of what was presented today, especially in terms of, you know, having that common foundation and that stable kind of base to build all of your stack on, whatever your application is. And I think, you know, some of the things we've heard about, you know, the different form factors under things like SOSA or under some of the other emerging standards, as well as just the general idea of, you know, if you have that common foundation, you know, use the best tool for the job, right? There's another question about unmanned vehicles and SWAT profiles, same kind of concept, right? Whatever's going to fit for that application, as long as it can talk to others in its domain or across domains, you know, you've got to be able to find the flexibility and the adaptability at the right price point, of course, especially in the non-defense applications, to make it work.
Absolutely. Anyone else want to add to that open-ended, forward-looking?
I'll add one thing. So originally, MOSA, really SOSA came out of the desire of the military to have a quick upgrade path, because that was their main complaint. It took many years and great expense. You know, if people would, you know, companies would get bought out, sometimes they couldn't upgrade for any kind of money. So this is really trying to catch up with the rest of, say, the computing industry, where they have had standards like this. So, you know, the industrial standards are out there already. So I think that the military is actually trying to catch up with them in many ways and get to that point.
That's true.
Yeah, and even on the computing side, it's a good point. Just in the commercial computing world, you know, there are standards like USB and gigabit Ethernet that are common, you know, buses and architectures that are widespread across. So you have these non-proprietary, kind of locked, you know, as an example of that. And so that type of approach, however it's abstracted for whatever application makes sense, I think is kind of the backbone here.
For sure. Definitely. And we have 2 more questions left. So I'll just leave these open to whoever wants one, whoever wants to provide insight. This one says AMS and DRTI developed a 100 millimeter VPX concept for SOSA plugin cards. I guess Robert, has Mill Power looked into this and considered whether or not they could produce Vita 62.0 3U SVPX form factor versions of these modules?
Yeah, I think you're referring to the short VPX that Mark was talking about earlier. So yeah, we're looking at that. It's in principle they're very much the same thing. It's just a double stacked, something that's twice as fat basically in a smaller form factor, smaller but fatter slots to us. So we're looking at it. It's a little challenging with power supplies. We have tall, ugly things that that may not want to stack as well as say a nice digital solutions out there. But yeah, it can be done. We're looking at it.
Absolutely. And this is the final question. So if any audience members have any other questions that they want to submit while this one is being answered, feel free. Unmanned vehicles will be pivotal in joint domain operations, being that the platforms can be on the smaller side. In what ways will MOSA and SOSA adapt to cater to smaller platforms while still supporting the JADC2 initiatives? And Craig, if you want to take that one away at the start.
Sure. So, in the smaller platforms, it is very difficult to, build a powerful computer that can ingest all the content that's being pushed from the sensors. And there's LiDAR, and some have radar, some have EO, and some have IR at a price point that's affordable to go on a $250,000 UGV. So it's critical. And I think Systel does a great job of it, especially when we incorporate technologies that are built on what they call a systems on module. Being able to ingest all that content, process it, and then more importantly, be able to push it up that ecosystem so the JADC engine can start to ingest it, can start to interrogate that content and build a common operating picture. So it was mentioned earlier, these smaller systems like ours, they don't necessarily feed the ecosystem, but in reality, we're the brine shrimp of the JADC2. We're the beginning of the food chain. We feed content to this big giant blue whale that actually processes it. So, when I talk about MOSA, and by the way, MOSA is not SOSA. MOSA is a philosophy. SOSA is a technical requirement. So when I talk about MOSA for us, it's when we pull in the GCIAs, the SAVEs, some of the other open standards to accommodate for things like this. Small form factor, low price, feeding content to the JADC2 beast.
I like that.
Emma, if I could add to that, though, and firmly wearing my small form factors subcommittee chairman hat in SOSA, it's absolutely central to our charter that we whatever we come up with in that subcommittee is in alignment with SOSA principles. And so everything that we're doing, we always have to test against those principles to make sure that we're not breaking something, that we're not doing something that doesn't support the overall SOSA mission. So just being small doesn't mean you can't be in alignment there.
Absolutely. And just to clarify as well, I jumped right in and started using acronyms. So JADC2 is Joint All Domain Command and Control, for anyone in the audience who wasn't aware, probably arguably the primary multi-domain initiative in the military at the moment in time. But we just got one last question in from the audience, and we'll use this as our wrap-up question as well. So I'll delegate it to anyone interested. The audience member asks, one vision of MOSA is convergence of disparate systems. How do we address any user complexity that may result from the convergence of several disparate systems and capabilities?
So I'll take that because I have an idea who asked the question. So one of the biggest challenges that Systel had a couple of years ago was we built the rack mount servers to support Minotaur. And the challenge with Minotaur was all these disparate systems on the P8, and then being able to put all of the output from the sensors in a coincidenced format. So the operator doesn't get, you may have an IR camera reporting at 60 hertz and a LiDAR reporting at 8 hertz. In theory, that camera is going to see the same target 5 times opposed to the LiDAR. So the challenge for us and how we resolved it was we used a converged architecture based on an open standard. The standard was ATX, and in a nutshell, we integrated multiple GPUs, multiple sensor capture types, video encode, video capture, processing, storage, and RAM to support this in a single 4U box. So it's hard. It's software obviously focused, but it was critically important that we used a converged architecture, basically everything in one box, to be able to meet that challenge. And Minotaur, by the way, is part of, or elements of Minotaur support JADC2. So putting content in coincidence is extremely critical. I hope I answered the question. And whoever answered that, I know who you are. I'm going to find you this weekend.
Anyone else want to throw in their last 2 cents before we wrap up? No? All right. Well, those are some great questions from the audience. Thank you so much. And that brings us to the end of our Q&A portion and to our time limit for session 3. I'm sorry if we couldn't get to all of your questions today. However, someone may get back to you after the event with more information. I would like to give a big thank you to Mark, Anish, Craig, Robert, and Jason for speaking today and providing everyone in attendance with such valuable insight. And I would also like to thank Elma Electronic, Systel, Mill Power Source, and Curtis Wright for sponsoring this session, and RTI for sponsoring the overall event. This and all Open Systems Media virtual events are copyrighted and may not be recorded or used in any way without the express written consent of Open Systems Media. This session and overall event will be archived online today and will be available for 1 year. There will also be an MP3 version of the event available. Thank you for attending the MOSA Virtual Summit, and we look forward to seeing you on future events.
Thanks.